concluding now section 3.6, we'll look at example 5 as an example that will help us to summarize many of the things we've discussed in this section. And example 5 says, sketch the graph of the rational function by hand. First find all intercepts and asymptotes. What I'm going to do is scroll down here a little bit and do some work down below what you see in the current view, and then we'll fill everything in after we've done some of our preliminary work here. The first thing we might notice is that it's possible to factor both the numerator and the denominator, and if you can do this sort of thing, it should be of use to you. It should make things a little easier to handle. So our function, let me just recopy it down here first. It's x squared minus 4x plus 3 over x squared minus 2x. Now the numerator factors as x minus 1 times x minus 3. The denominator factors as x times x minus 2. One thing we notice right off the bat after factoring is that there are no common factors. In terms of vertical asymptotes, set the denominator equal to 0 and solve for x. That's easy to do. X equals 0 is one solution, and x equals 2 is a second solution. In particular, x equals 0 would be the equation of the y-axis. So there must be two vertical asymptotes of this rational function. The y-axis is one of them, and x equals 2 is a second one. Okay, what about horizontal asymptotes? Well, there it's a question of comparing degrees. The degree of the numerator is 2. The degree of the denominator is 2. If the degrees are identical, then there will be a horizontal asymptote, and its equation is determined by the ratio of the leading coefficients, which in this case are both 1. The equation has the form y equals a constant, and that constant would be 1 because 1 over 1 is equal to 1. So there is a horizontal asymptote, y equals 1. That's the only horizontal asymptote. There can be no more than one horizontal asymptote for a rational function. And since there's a horizontal asymptote, there can't be a slant asymptote. Indeed, slant asymptotes only occur when the degree of the numerator is 1 greater than that of the denominator, and obviously that is not happening in this case. So we've taken care of vertical asymptotes, horizontal asymptotes. How about intercepts? Well, for x-intercepts, you're looking at where f of x, or y, is equal to 0. That means where is the numerator equal to 0? Well, take the numerator, x minus 1, in factored form, x minus 1 times x minus 3, set it equal to 0, solve for x. You get x equals 1 or x equals 3. Those should be the points at which the graph crosses the x-axis. Points of that sort are useful to know, of course. Now, these are not vertical asymptotes, so let's write them as ordered pairs. X equals 1 is actually just the single point 1, comma 0, and x equals 3 is just the single point 3, comma 0. So better to write them as points here so that we don't confuse these values of x as being vertical asymptotes as being lines. They're just actually single points on the x-axis. What about a y-intercept? Well, the y-intercept is determined by setting x equal to 0. But we've already seen that 0 causes division by 0. 0 is not in the domain of our function. The domain of our function is all values of x not equal to 0 or 2, where the denominator is equal to 0. So since x equals 0 is not in the domain of our function, there is no x-intercept. The graph does not cross the there is no y-intercept. The graph does not cross the y-axis. After all, we already stated that the y-axis is a vertical asymptote, and the graph of a rational function can never cross or touch any of its vertical asymptotes. So there is no y-intercept for the graph of this function. Let me now indicate on the graph what we have identified thus far. There were two vertical asymptotes. The y-axis is 1. Since the y-axis already appears, there's no need to indicate it as, to actually graph a line for that asymptote. But there was a second vertical asymptote, x equals 2. So I'm going to indicate that as a dashed line, a vertical dashed line passing through x equals 2. So that's our second vertical asymptote. We also identified y equals 1 as a horizontal asymptote. So that would be the horizontal line passing through y equals 1. So you want to get those asymptotes sketched in there first. So we have x equals 0, that's the y-axis, x equals 2, and then the horizontal asymptote y equals 1. We also noted that there are x-intercepts at 1 and 3. So there's going to be an x-intercept at 1, 0 and an x-intercept at 3, 0. There is no y-intercept. What's basically left at this point is to identify some additional points. And what I've done is created a table where I've selected some values of x sort of between and beyond some of the key features we've already found. That would include vertical asymptotes and x-intercepts. So I have some values of x to the left of x equals 0. That would include -4, -2, -1. I have some values of x between x equals 0 and x equals 2. So the ones beyond the y-axis would be the negative values here. Then I have the values between 0 and 2. That would be 0.5 and 1.5. Just trying to identify some additional points so I can get an idea of what the graph does. And then some points beyond x equals 2 to the right of x equals 2. We already have x equals 3 as one of those, so I also chose 2.5 and 4. These were just values of my own choice that I thought would be useful in determining what the graph was doing in different parts of the xy plane. Essentially, there are three separate pieces to the graph because of the two vertical asymptotes. So the two vertical asymptotes divide the graph into three distinct sections that don't have any points in common. So what we have to do then is find the y values associated with the values of x. And I'm not going to go into great detail for this, but let me just show you how I would compute one of those values. If I want to compute f of -4. Now I could substitute into the function in its original form, but we might find it easier to use the factored form, x minus 1 times x minus 2 over x times x minus 1 times x minus 3 over x times x minus 2. And so substituting in negative 4, there we would get negative 4 minus 1, negative 4 minus 3, and then that's all divided by x, which is negative 4, and negative 4 minus 2, x minus 2. So what I would have is negative 5, negative 7. Bear with me one moment, please. Okay, so we have negative 5, negative 7 over negative 4 times negative 6, or 35 over 24, and 35 over 24 is approximately 1.5 to the nearest tenth. So as you can see, it's kind of tedious to do all of this by hand. If you had a graphing calculator with a table feature, you could easily find additional function values and let the computer do the let the calculator do the grinding out the specific computations. So I'm just going to fill the table in for you so you can see what the other values would give us. But this is essentially how we could do it by hand if we needed to. So let me complete this. The table at negative 4, recall I showed you this one. We got 1.5 approximately. For negative 2, you would get about 1.9. Negative 1, about 2.7. 0.5, negative 1.7, 1.5, 1, exactly 1. 2.5, about negative 0.6. All of these are rounded to the tenths place if necessary. And at x equals 4, 0.4. And then I'll do my best to plot these points. So we have a negative 4, 1.5. Okay, that would be about there. Negative 2, 1.9. Okay, that would be about there. Negative 1, 2.7. That would be approximately there. 0.5, negative 1.7. That would be 0.5, negative 1.7, about here. Then 1.51, that point is actually right on the horizontal asymptote, but remember a graph can cross a horizontal asymptote. 2.5, negative 0.6, negative 0.6, about there, and 4.4, about there. And then the other thing I need to note is that the asymptotes sort of determine where the different pieces of the graph are going. So there'd be a piece going up there to the left like that, up along the y-axis here, down along the y-axis here, up along x equals 2 here, down along the line x equals 2 here, then up towards the horizontal line y equals 1 here. And then we'll just connect the points themselves with smooth curves. So let me do that next. So I just paused the video for a moment so I could sketch in the curves, and you can see what the final graph looks like. Obviously, this method of doing everything by hand can be kind of tedious, especially when it comes to plotting all of those points. But it does help you to kind of see how the graph sort of all comes together, how the asymptotes affect the shape of the graph, how the asymptotes cause the graph to kind of stay confined within certain regions of the plane. So this is not going to be something of great emphasis, graphing complicated functions by hand, but it's good to at least see one example of this to kind of give you more of a concrete illustration of graphing rational functions.